Okay, YouTube, in this video we're going to continue our exploration of graphing exponential functions. And so you can see that I have a couple of exponential functions that I want to graph here. In this video though, I want to point this out. In each instance though, when we look at our exponential function, our positive constant that's not equal to 1, that is our base. Both of these are proper fractions. And so what I want to kind of confront is how this affects our graph. So the first argument we're basically going to make here is this, that 1 over 2 to the x is the same thing as 2 to the negative 1. Remember that 1 over 2 to the positive 1, if we move this 2 back upstairs, it becomes 2 to the negative 1 over 1. But these mean the same thing, and using our rules of exponents here, we would say a power to a power, you would just multiply your exponents. So I suppose the first thing that I want to write here is that this is the same thing as 2 to the negative x power right here. These two functions are the same thing. And so that being said, what I know is when we talk about transforming the graphs of functions, if I were to graph 2 to the x, I would get some function that goes through 0, 1, and 1, 2, and looks like this. This was a crude sketch. But basically what I want you to see is by taking that parent function and putting a negative in front of your x, what we're going to get is something that reflects over the y-axis here. And so certainly when we explore this, let's go ahead and do what we normally do, but we're going to plug it into, say, this function right here. So we say g equals 1/2 to the x power, which is the same as 2 to the negative x. If we were to make a table of values, let's go ahead and start with this. We say x, and we say g of x. And we get -3, -2, -1, 0, 1, 2, and 3. Let's start by plugging in 0. And if we were to take 1/2 to the 0, we would totally get 1. Of course, it would go through 0, 1. This is a pretty common to all exponential functions. Now, if I take 1/2 to the 1, I actually end up with a half. And 1/2 to the 2 is a half times a half is a fourth. And a half to the 3 is an eighth. And when we go backwards this time, when we take, say, 1/2 to the negative 1 power, that's the same thing as 1 to the negative 1 over 2 to the negative 1, which is the same thing as reciprocating both of these, 2 to the positive 1 over 1 to the positive 1, which is 2. So you'll notice that we get 2 here for our negative 1, where with 1 we got 1/2. We're going to end up with reciprocals again in this particular instance from what we have down here. And when we graph these in, we say 0, 1, for instance, we'd also graph 1, comma, a half. 1, comma, a half would be here. 2, comma, a fourth, and then 3, comma, an eighth. And going backwards, at -1, we're at a height of 2. At -2, we're at a height of 4. And at -3, we're at a height of 8. So what we get is a situation like this. Just like in our last examples when we had exponential, what we called growth, we're going to refer to this as exponential decay. And we can see that from left to right, our graph is actually approaching the x-axis and always decreasing here. So really quickly, let's graph 1/3 to the x. I suppose if I was going to graph 1/3 to the x, I know that there's going to be an asymptote on the x-axis here, so I'll go ahead and fill that in. Whoops. Asymptote on the x-axis. I'll get back over to here. We say at y equals 0. When we plug in all of our points here, I think that we want to be getting used to this one point instantly here, but our y-intercept is always when we plug in 0 here. And when we plug in 0 for x in this case, we get 1/3 to the 0, which is 1. So of course we expect our graph to go through this point 0, 1. Now if I plug in 1, 1/3 to the 1 is a third, 1/3 to the 2 is a ninth, 1/3 to the 3 is a 27th. And if we go backwards here, this will be 3, this will be 9, and this will be 27. And if you're unsure about this, you can certainly feel free to take 1/3 to the -3, for instance here, which would be the same thing as 3 wholes to the +3, which is our still 27 right up here, okay, if we were to use -3 for our input. So our graph, let's go ahead and put these points on the grid here. -3, 27 is too tall for me to put on this grid. But we say -2, 9 would be here. -1, 3 would be here. And then we have, of course, a third, a ninth, and a 27th. You see that it's getting really close to the x-axis as we go to the right there. Okay, so we get something that looks like this right here. And so domain on both of these, let's go ahead and talk about this. For all exponential functions, every single one, we admitted that we can plug in any x value that we want for the exponent. In terms of the range though, I'm seeing on both of these that their ranges are 0 to infinity and 0 to infinity. What I'm going to argue is, of course, that our range would be all of the y values either above or below the asymptote depending upon where your graph is. So what I want to do is I kind of want to generalize what we've seen up until now. So here we have 4 different exponential function graphs. So we have this kind of this red one, this blue one, this green one, and this black one. But what I want you to notice is for all of these graphs, they all pass through the point 0, 0.0, 1 is common to all functions. So any function that is of the form y equals b to the x, where b does not equal 0 and b does not equal 1, we're always going to have it go through the point 0, 1. Now, as far as these two graphs that go uphill, you can see that this green one that is really taking off pretty quickly, it goes through the point 1, 7. This is this y equals 7 to the x, where this is y equals 2 to the x. So these are both growing as we go from left to right, or moving away from the x-axis. But that's because our base are what they are. Our bases are what they are. When you look at the bases of these other two here, these are not growth. I would refer to these two over here as decay, where these two are growing. But basically, these are decaying because you'll notice here that when I have y equals 1/2 to the x, that's the same thing as 2 to the negative x, which is really 2 to the positive x, but reflected. I don't want to write that there because I'm just going to take up my room that I need over here, but it's reflected over the y-axis when we make our x values negative. So what we're going to notice here is this. We say, what do they all have in common? All pass through 0, 1. And if anybody says explain this, just go plug in 0 for x and see that anything to the 0 power is 1. Also, we want to say this. All have a horizontal asymptote at y equals 0. Or we could say the x-axis. Okay. So in terms of what's different about them, they are not changing at the same rates. Okay. Some of these grow faster than others, and some of them decay faster than others. Okay. We can say, how can we tell from their functions which graphs will rise from left to right and which graphs will fall from left to right? So in terms of rising, I notice that these two functions here, the bases are 7 and 2, whereas if they're falling, I get 1/2 and 3/4. So what we'll say is this. For y equals b to the x, if b is bigger than 1, then we're talking about growth. We are going to rise as we go from left to right. And if b is a proper fraction, that is, if it's between 0 and 1, we're going to say that we get decay. And these are the only two possibilities that we can get here, and it's easy to recognize just by looking at the function. So characteristics of exponential functions, I got to be honest with you, there are two of them that are pretty consistent. We'd say that yes, we go through 0, 1, and we have this horizontal asymptote on the x-axis. So you'll notice here from our picture here, we say y equals b to the x if b is a proper fraction. If your base is a proper fraction, you are going to decay from left to right, or you're going to fall from left to right. And if b is bigger than 1, or an improper fraction, we have a growth from left to right, which is what you see with this blue graph right here. So all of this right here, this table, basically says everything that we've been saying here, that our domain is all real numbers, our range is always either above or below the asymptote, and we go through 0, 1, and we also have an asymptote on the x-axis there. Cheers.